Now, moving on in chapter 12, if we want to utilize some of our primary or secondary alcohols via an SN2 reaction, we can't use HBr or HCl. We have to use some other Lewis acid-base chemistry rather than the Bronsted-Lowry acid-base chemistry we saw before. So with primary and secondary alcohols, if you want to undergo an SN2 reaction, you will use one of two reagents. If you want to make an alkyl chloride, you would use the SOCl2 thionyl chloride. Or if you wanted to make the alkyl bromide, you would use PBr3. And so when looking at these two reagents, they do not have a proton transfer as their first step. They will be making oxygen as a better leaving group. However, they do it in a different way. Let's go ahead and take a look. Now, the thionyl chloride mechanism starts us off by understanding that oxygen is a nucleophile, sulfur is the electrophile, and we do a nucleophilic attack. We have to kick up the pi bond electrons onto that oxygen so that we don't break the octet. We know sulfur can expand its octet, however, pi bonds are easily movable into lone pairs. That's when the oxygen will roll its lone pairs back down to become a pi bond and kick out Cl-. Now we're almost at our good leaving group, not quite yet. If you cover up the carbons in this molecule, think about this functional group here. It almost looks like sulfuric acid. So we would not want this to be our leaving group, which is why we need pyridine. Pyridine, that Py up there, has been used before. It's a base. It's a really good base. It's nitrogen in that six-membered ring, and it will do a proton transfer so that now we have our good leaving group. Oxygen can leave with a minus charge, and it has resonance. So what actually happens here is Cl- will come in, backside attack. Oxygen, instead of taking that negative charge, will actually kick over that carbon-oxygen bond to make a new oxygen-sulfur double bond and kick out a second equivalent of chlorine. Now what this produces is SO2. Looks like this. It's just what we made when we instituted that second sulfur oxygen double bond. SO2 is a gas, and so it bubbles out a solution. We know that anytime we produce a gas, this drives the reaction forward because of La Chatelier. The equilibrium is disturbed because the product is bubbling out of the solution, so the reaction will proceed to make more products. And so there's your SN2 style backside attack. Again, this works on primaries or secondaries. Because tertiary alcohols cannot undergo an SN2, you would never want to use thionyl chloride with a tertiary alcohol. PBr3 mechanism is very, very similar. We have oxygen attacking the phosphorus and kicking out one of our bromines. Now this is already a good leaving group. It's not acidic. And so the Br- can come back into that backside attack and kick off that leaving group. There's your leaving group. And there's that SN2 reaction again. Moving into oxidation of primary alcohols. Now with a primary alcohol, because there are two protons on that alpha carbon of the alcohol, there are two steps to the oxidation. We can first become an aldehyde, which again is an oxidation. We're making a new carbon-oxygen double bond, and we are decreasing the oxidation state of carbon, losing electrons, oxidized. We can go further and make another oxidation step to where that second proton gets lost, and we oxidize the carbon even more. And so we would become a carboxylic acid. It's very important to recognize that primary alcohols have 2 points, either the aldehyde oxidation or the carboxylic acid oxidation, because we'll see different strengths of oxidizing agents. So the stronger the reagent, the more likely we are going to fully oxidize that primary alcohol to the carboxylic acid. If we use a weak oxidizing agent, we can stop at the aldehyde, and so we'll see that momentarily. Secondary alcohols, because they only have one proton, there is only one way to oxidize them, to the ketone. And then we stop. There's not another further step. We cannot oxidize past that secondary alcohol to the ketone because of the ability of only one alpha hydrogen. Just as a note, what does that mean? Tertiary alcohols do not undergo oxidation. So if we think about oxidizing them, because a tertiary alcohol has no alpha proton, no alpha hydrogen there, there is no reaction with tertiary alcohols here. You need at least one alpha hydrogen in order to get this oxidation to occur. So most common oxidizing agent is chromic acid. It's formed with either CrO3 or sodium dichromate, Na2Cr2O7. Now, in an aqueous acid, either one of these will form chromic acid, which if we abbreviate H2Cr O4. Chromic acid is also called the Jones reagent. Most often what you will see over the reaction arrow for our class is either sodium dichromate or with acid or automatically chromic acid. These are very, very strong oxidizing agents to be able to oxidize the alcohol. Now, we aren't going to go through the mechanism, but what we should know is that chromic acid is a strong oxidizing agent. And so it's the first step right there is fast and reversible. When we think about the oxygen, we can do a pseudo mechanism here. This would not be required on an exam, but you would do a pseudo style mechanism. It's not exactly that because we do have a proton transfer. This guy and this guy come together to make water. But it is where the alcohol oxygen will be attaching to the chromium atom to make a chromate ester. And then we have an E2 mechanism. This is the mechanism I do want to show, where the water comes, pulls off an alpha hydrogen, right? The alpha hydrogen being the one that was on the actual alcohol. That electron goes to make the new carbon-oxygen double bond. And it also kicks off the chromium with the lone pair as the leaving group. And so with this, we are making a new double bond, but it just happens to be a carbon-oxygen double bond. This would be the formation for a secondary alcohol into a ketone. Now, chromic acid will oxidize that primary alcohol straight to the carboxylic acid. We cannot stop at the aldehyde. Chromic acid oxidation is very, very reactive. So it goes straight from the primary alcohol to the carboxylic acid. Through the aldehyde, yes, but the aldehyde is an intermediate that is not isolated. We will only see the carboxylic acid as our final product when we use chromic acid oxidation. Now, PCC, pyridinium chlorochromate, you see it over here. I want to kind of think about this as a less reactive oxidizing agent. Notice how there's a lot of stuff going on, very similar to Lindlar's catalyst when we talked about hydrogenation of alkynes. Pyridinium chlorochromate, PCC, is an oxidizing agent. However, it is less reactive. And so what that means is that we actually can take that primary alcohol straight to the aldehyde and stop at the aldehyde. PCC will not oxidize aldehydes further to the carboxylic acid. so we can actually prevent further oxidation there and only see aldehydes as our final product with PCC. Dichloromethane CH2Cl2 is just a solvent. It's to make sure that we're not in water. And so just noting that that solvent is polar aprotic. So regardless of the oxidant used, either chromic acid or PCC, the secondary alcohol, because there's only one oxidation product, either one of these will take a secondary alcohol to a ketone. It's, again, the mechanism is not one that I would require you to understand. Just know the transformations. All right, so just to clarify here, I wanted to show, similar to what we just saw with the secondary alcohol, here's our alpha. It's a primary alcohol, ROH being that functional group condensed structure there, using chromic acid, very reactive. We will take both of those hydrogens on the alpha carbon, and what we make out of at the end of the day is a carboxylic acid. PCC is a mild oxidizing agent, so we end up with the aldehyde. Excellent. Again, transformations only, no mechanisms for either of these. Like PCC, the Swern oxidation also converts primary alcohols to aldehydes. The only reason to know this one, there's a couple other options for oxidation in the textbook, but they all do the same thing as PCC. The reason why we have an alternate here with the Swern oxidation is due to the fact that chromium reagents are highly toxic. A lot of my work in industry before I started teaching was dealing with ultra low levels of hexavalent chromium, which is a very bad thing to have in drinking water. But due to some industries that do not have stringent enough rules about dumping chemicals, chromium reagents have gotten into the groundwater and therefore into drinking water in some cities. If you've ever watched or read the story of Aaron Brockovich, you would know the health hazards with hexavalent chromium in the water. And so using chromium reagents is very stringent in research labs. And so this is just an alternate. The Swern oxidation uses DMSO, dimethyl sulfoxide, and COCl2 there to oxidize. And you use triethylamine to kind of be the base to work up that final step. Again, only the transformation. You would not need to know the mechanism itself. It's in your textbook. If you want to take a look at it, go for it. However, we will not cover it. All right, so let's just look at what we have here with predicting products for the reaction. We have a reactive oxidizing agent. This is another way of writing the chromic acid oxidation requirements. So let's just look at all the alcohols we have. We have a secondary alcohol, we have a primary alcohol, and we also have an aldehyde. Now remember, chromic acid oxidation oxidizes all carbons to the fullest extent. So we have our carbon chain here, and what we need to think about is the secondary alcohol will become a ketone. The primary alcohol will become a carboxylic acid, and the aldehyde will also become a carboxylic acid. Take a minute to review that to see all those transformations.